Hello and welcome. Today I want to talk about Bayesian estimation theory. In particular, I want to talk about first the concept of a loss function and about how we evaluate a loss function. Then I want to take it three very important examples of loss functions and of Bayes estimators. Finally, I want to make a connection back to game theory and to frequentist parameter estimation. Let's start with the first topic. Remember that we have some value, some random variable theta, which is going to take some value, and we have a sample x. And we want to estimate something. In our particular case, we are going to want to estimate theta, but really sometimes we want to estimate a function of theta, and in a very general sense, we just want to make a decision based on our sample. So I'm going to define this very, very broadly, and this is the usual way of how it's defined. I'm just going to have a function delta of x, where delta is a function mapping from the sample space to what's called the decision space, D. D can be literally anything. It represents that decisions that we make based on our sample. It doesn't necessarily have to do anything with theta. In some sense, it definitely will, because otherwise, why do we care about why do we make this model with theta? But it's more about it's very related to the real world. For example, in our first example, where we had this, if we go back, we had this example of theta, the true value being us being sick from a disease or being healthy or not sick. The decision space, for example, could be the space that contains two decisions. Either we go to work, probably because we think that we're not sick, or we stay at home because we think that we're sick. And we're going to base these decisions based on X. What is X in our case? It's the test result. So remember, in the example in the very first video, I guess in the example was a patient made a test, and based on this test result, we were guessing, is the patient sick or not? But that's not, it kind of is the question that we care about, but really we want to make a decision. We don't just care about the fact whether we're sick, we care about what do I do now? What is my decision now that the test gave me this result? Do I go to work or do I stay at home? For example, how do I evaluate this decision? I'm going to evaluate it via a loss function, L, which compares our decision. Well, it doesn't compare it, but it tells us the loss that we make based on x given some value theta. The loss function, it's always larger or equal to 0. So the higher the values, the worse our losses are. What would this mean in our case? Well, it depends entirely on us. There are several cases that can happen. We could, for example, be in fact sick, but go to work anyway. What are the consequences of this? Entirely depends on the situation. In the case of, if we take the most famous disease right now, which would be COVID, the consequences could be that somebody else catches COVID and then they also have to quarantine. We have to quarantine, and we could say that that's a huge cost for us because we don't want that to happen. Another argument could be, it entirely depends on how serious you take this case of us going sick to work. You could just as well make an argument that it wouldn't be so bad. Maybe you're going to a job where you're not interacting with anybody anyway. I don't know. I'm not making that case at all. I'm just making an example. So in this example, let's say for some reason it's really it's a horrible consequence to us, and we have to somehow give this a number. And this gives us the first idea of why loss functions are sometimes kind of problematic. We don't really know what number to put on this. Because, okay, we know that we might say that it's pretty bad, but how bad exactly is it? And if you want to define a loss function, you need to say how bad exactly is the case of us going to work, even though we're sick. So, for example, we can say it's 1000. So let's say that it's 1000 because it's 10 times worse than the alternative error of us being healthy but staying at home. Why is that a loss? Staying at home? Well, because we actually want to go to work, and if we stay at home, we miss an important meeting with our boss. We can't go outside. We have to stay at home and just lay on our bed and panic, and that's awful. Something along those lines, whatever. And then we could say we made a mistake because we stayed at home even though we were healthy. On the other hand, the other two cases, if we assume that if the test result is actually accurate, that our best decision would be to stay at home if we're actually sick, and also our best decision would be to go to work if we're healthy, we just set the loss function to 0. Okay, now we have a loss function. What do we do now? We are in the case of theta being a random variable. So theta is random, and this means that theta could take any one of these values. So we have to find a way to make a decision even though theta could, even though there's no like optimal choice. For example, here we can't say we go to work no matter what happens, because there's some cases where we want to go to work, but there's some cases where we stay at home and we don't know which one. And the usual way to deal with these kinds of things is to take the expectation of the loss function. And we are dealing with the case of Bayesian statistics here. So we want to make our decision, not only make our decision be based on theta, but we also want our loss to be based on theta. So we take the expectation based on the posterior distribution given x, which is the conditional expectation given x. And this is how we define a Bayes estimator. A Bayes estimator is an estimator delta hat such that we minimize this expectation that the head of x is equal to the minimum over any delta of this expectation. Okay, so we defined loss functions, and now we're going to actually look at some examples where we find base estimators to the most common and very important loss functions. I'm going to focus on estimation theory. Estimation usually means, I know I talked about this a bit broader in the introduction, but usually estimation theory means that we want to estimate theta. This means that the decision space is just equal to the parameter space. Delta of x, the best value that it can have is theta. And actually the loss function, whenever delta of x hits theta, it should be 0, because we can't get any better than that. So how can we evaluate our loss? One way, and the most common, is to define the loss function as the quadratic error. Why is this the most common way? You'll notice that the expectation of this loss function, given x, is just the squared expectation. The expectation of the square. And expectation of squares are very nice. They're very easy to deal with because they're very closely related to the variance, and we know a lot about the variance. This is one way to think about it. Another way to think about it is to think about this as some kind of distance. Quite literally. When you think about it, when you have 2 points, A and C, let's say the two lengths A and B, and the points are big A and big B, then the distance between A and B is A squared plus B squared, and you need to take the square root of that. So in this sense, actually, really, if we take this image and take a very similar image, what we're doing is, again, we have some coordinate system, but not on numbers, but on functions. And we have this value theta, which in our case is a function because it's a random variable. We want to find a value that's very close to theta. But we can't just take theta, we have to choose from this space, which I'm going to draw. And this space is the space of all functions delta of x. And in this space, we want to find the point with the closest distance to theta. We do that exactly like we do it with usual geometry. If you look at this point theta, our best estimator, the estimator with the shortest distance, delta hat, should fulfill the fact that this line, I should draw it in red, this line right here, it's a right angle. Not only to delta hat, but actually to every element in the space. And what is the line? The line is just theta minus delta hat, right? So we know that the angle is a right angle. This just means that the scalar product, in our case literally the product, well, the expectation of the product between theta minus this best estimator, which we don't yet know, and any other estimator, delta of x is equal to 0, given x. Keep forgetting the x. So if you have trouble with expectation of something given x, it just means that we treat x as a constant, basically. These values here, they're basically constant. The only thing that's actually a random variable is theta. So we can plug everything out. This here, we can plug it out. Same as this here, we can also plug it out of the expectation. And what's left is the expectation of theta given x. So what I mean is, first we plug delta of x out. Then with delta of x times the expectation of theta given x minus delta hat of x. And we want this to be 0 for any estimated delta. How do we do this? We just set delta hat of x to be equal to the expectation of theta given x. And that's our first estimator. That's actually how the conditional expectation can be defined. It's the best estimator that we have in this field here if we want to minimize the squared distance. This is good if we are actually thinking in terms of distance. For example, if we want to minimize the literal distance of the length of our drive to the next city, or if we think about minimizing some monetary loss, something that we can actually interpret in terms of distance is very useful. A bad example of using this loss would be, for example, if in our testing example we only care about whether the test is positive or negative. That's the 0-1 loss, but even though this is a very nice way to change the topic, I'm actually not going to talk about the 0-1 loss, because first I want to talk about something very similar to the squared error, which is the absolute error. The absolute error is exactly what it says, the absolute distance between delta of x and theta. Again, we want to calculate the base estimator, so we want to find some delta which minimizes the expected error given x. Again, just as last time, I didn't technically prove anything for the squared error, although it was very close to prove. Same as in this case, the actual proof, it's not difficult, but it doesn't give a lot of intuition. So I'd rather give a lot of intuition and explain what might be going on. If you want to prove this, I recommend just trying it and looking at the different cases. I think it's very doable, but it's very technical in some sense. So I'm going to leave that out. But as an intuition, I first want to draw a picture of the absolute value of theta minus some c, some constant c. Let's say c is here. What does the absolute value look like? If theta is bigger than c, so let's say it's theta, we just have a line. We grow linearly the farther we go away from c. Same thing if we go to the left. Now, I just want to look at the finite case. So let's say theta, it can only take so many values, theta 1 up to theta n, for some n. Then if we look at the expectation, we can calculate it directly. It's just the sum over all possible values, where we have the probability. So I guess I should say theta given x only takes these values. So we take the probability that theta is equal to this value given x times the distance of this value and delta of x. So for every value here, I have this curve and I'm stacking these on top of each other and I'm weighting them by their probabilities. And so let's say I have the simple case of an even simpler case of this probability actually being equal to every other probability, and it's just equal to 1 over n. Then if we just take the example of the numbers 1, 2 and 3, we basically stacking these three curves on top of each other. So if we're left from 1, we're increasing linearly left from 1 with a slope of 1. Same thing, because we're left from 1, we're also at the left side of 2 and 3. So our slope here is going to be very steep. Is that the right word? I'm not sure. It's a very high slope. We go to 1 very, very fast. But once we hit 1, all of a sudden we're on the right side of 1. So if we just look at the triangle independent of the other three values, now it goes up. The other two curves still go down because we're on the left side of 2 and the left side of 3. So we're still falling, but we're falling much slower because we don't have a slope of 3 anymore. We have a slope of 1 plus 1, which are the slopes of that 2 and 3 are contributing, minus 1, which is the slope that 1 is going to contribute. So we have a slope of 1. We're falling much slower until we hit 2, and then on the right side of 2 we have the exact same situation but mirrored. We have a slope of 1, minus 1, minus 1. So we're going to the other direction. I'm just realizing that I have the wrong direction for the slope. So here we have a negative slope. On the other direction we have a positive slope. It doesn't matter, it's the same thing. See, again, we have a straight slope up. This should be symmetric if I could draw it correctly. And then we have a very high. We just keep increasing really, really rapidly. So our minimum is at 2. And this is because at 2, there's just as many values on the right side as there are on the left side. If we would be weighting these values differently, we would still have to find the balance between the weights. So we can weight them differently if they have different probabilities, but we still have to find this balance because every slope has exactly this weight that we assign it. Right here, every slope has the weight 1. So you could say every point contributes equally to this loss times its weight. And the weight is, it's either its likelihood, well, it's actually, it's either his density or his mass, depending on if we're in the discrete or the continuous case. So in total times its likelihood. And so since every point contributes equally, we want to find the point at which the probability that we are smaller or equal to this point is equal to the probability that we're larger to this point. So this is actually defined as the median of theta given x. Okay, now let's move on to the 0-1 loss. Actually, first I want to talk about when do you use the absolute error loss. If you look at this, whenever I add some value, if I add like the value 0 at this graph, it's going to add 1 to the right side and subtract 1 from the left side of the slopes. But if we add a lot of values, that's not going to make much of a difference. even if this value is really low or very high. So if we'd have the value minus 1000, it will still only change the slope by 1. Same going to the median. So the median, if we worry that in our data somebody messed up and we have some extremely high value for some reason, that could happen. We want to choose the median because the median is very robust against outliers. On the other hand, if we would have the squared error loss, our error doesn't increase linearly, but quadratically, and that one outlier can make a huge difference if it's sufficiently high, because our slope or the derivative for the quadratic increase, it depends on our value of x. Okay, now let's talk about the 0,1 loss. If we remember our testing example at the very beginning, one could, if we don't know anything about our loss, one could just say, okay, let's say if we make a mistake, if we go to work when we're sick, or if we stay at home while we're healthy, this is gonna be a 1. So delta x is not equal to theta, it's gonna be a 1, otherwise it's going to be a 0. So the simplest way you can define loss, or in general you could say we have some area theta 0, some event about which you care. So maybe the event of us being sick, it's not just one value, but it's a huge set, and if there's a value in the set, if we make an estimation error and we are outside of the set, we say we give 1 and otherwise we give 0. Then we're talking about the 0,1 loss. And the 0,1 loss is very simple, but it gives a very, very nice interpretation about a very common estimator, which is the maximum likelihood estimator. Because if we look at this, let's say we have the discrete case. So in our very simple setting for testing, this here is just 1 times the probability that delta of x is not equal to theta, minus 0 times the other probability of us estimating correctly. We want to choose delta of x as the maximum of this probability right here. This is what's known as the maximum a posteriori estimator, and it just means we just want to maximize our probability of us making the right choice. This is for the discrete case. For the continuous case, we can't talk about the probability of this one being equal to exactly one value, because this is probability 0, but we can look approximately at the probability of this being, so I should write this out, approximately the probability of this being in some very small interval about around theta for a very, very small epsilon. This is going to be approximately the density evaluated at delta of x times this small epsilon. So if we want to maximize this, we can just, sorry, I guess it's 2 epsilon because it's the area. We want to maximize the likelihood in either case. But we can derive from this the maximum likelihood estimator by using Bayes' rule, because pi of theta given x, remember it's just this formula, which is proportional to, so by proportionate I just mean that we have this constant which we can discard, f of x given theta. And now if we also say that we assume a uniform prior, which we can do because sometimes it makes sense, this here is also a constant because the density or the mass function of the uniform is just a constant. So we actually have the case that the posterior is proportional to the prior. Sorry, not to the prior, but to the sampling distribution. And then we have exactly the definition of the maximum likelihood estimator, which is the maximum of the sampling distribution. And what's really nice is that in classical theory, I went a bit fast over the definition of the maximum likelihood estimator because usually people already know the definition. Usually, when you hear about this, it makes a lot of sense, but there's also no clear intuition for why it should work. Why should we want to maximize this probability? And here we have a very concrete reason, which is if we, for the maximum likelihood estimator, if we assume a uniform prior, which sometimes makes sense, we're going to talk about when it makes sense, then if we just want to maximize our probability of us being right, we should take the MLE. On the other hand, if we take any prior, any particular prior, we can take the maximum a posteriori estimate. Hi, me from post-editing here. I wanted to just mention one thing that I really regret that I haven't mentioned yet. And that is that we should still complete our example. So if you remember, we had a loss function for the test. Remember, we had this test where there's a chance that our delta of x is that we stay at home and while in reality we are not sick. And we gave this loss some weight, so I think we said 1000 or something, but I want to keep it a bit more general and say we have the weight A1. Same thing for the other error of us going to work even though we're sick. And then, okay, we still have a loss of 0 if we're doing everything right. If we're staying at home when we're sick and if we're going to work when we're healthy. And now with the theory that we've just established, we can actually calculate the conditional expectation. We can split this up in 2 parts. Either theta is equal to healthy given x, then we are penalized with the loss of A1 if delta of x is equal to stay at home. So we say we take this error if, and write this indicator function of delta x. If delta x is in the set stay at home. So that's one error, that's one thing that can happen. The other thing is that theta is equal to sig. Given x times our other loss a0, and again we have this indicator function, this time of the stat go to work. And we want to minimize this. So basically we have to decide, because delta of x has to take one of these values, we have to decide which one of the penalizations we want to take. So we just take the ratio and say if this ratio is bigger than 1, then we prefer to have the denominator as our error. So we set delta of x equal to go to work. In a less abstract sense, we go to work whenever this ratio is larger than 1. And this shows something, and also in a really nice way, shows something. It shows that first we have this ratio between the posterior probabilities. Which is very important, but equally important, exactly equally important, is the ratio between our penalizations. Not sure if that's a word. Between the way we penalize our errors. So even though it might be a lot more likely that we're healthy, if the cost of us going to work even though we're sick is very, very high, which could very well be the case, we could still decide to estimate, we could still decide to stay at home. This is very important and can easily be overlooked, that we base our decisions upon the test results, so we should also take our account the consequences of our decisions. And I just did this with the 0-1 loss, where we weighted things differently. We can do exactly the same with the absolute error loss. Where we say we have the p-weighted loss, if theta is larger than delta of x. And then we have the 1 minus p weighted loss if theta is smaller than delta of x. Or let's say smaller or equal. And this gives us, we weight things differently. And this also gives us different estimators. This gives us quantiles. So the median is a 1/2 quantile, and then quantiles, which I'm not going to define now, but there's something similar to the median, are given for this weighted loss. And we're weighting things because we want to penalize overestimation. In this case, for example, if p is large, we want to penalize overestimation larger than underestimation. If p is small, we want to penalize underestimation larger than overestimation. And we can do something very similar for the squared loss. And this also gives us slightly different solutions, which are pretty similar. We don't get the expected value, but we can, for example, get the weighted expected value, something along those lines. Okay, just something really important I wanted to mention. And now, please get back to the video. Okay, so we're done with our example. Let's finish with some connections to other parts of statistics. In classical statistics, one cares about minimizing the expectation of the loss function, not given x, but given theta. Because remember, in classical theory, theta is just some constant which we don't know. It's not a random variable, so it doesn't even make sense to talk about the expectation of theta given x, because it doesn't, theta is just a constant. And we want to minimize this for every theta. But if you look at this, you notice that if you take the expectation of this, so in Bayesian statistics, where we assume that theta is a random variable, this is just equal to the total expectation, which in turn is equal to the expectation over what we have been looking at this video, the conditional expectation given x. So already we have this connection between the frequentist risk and the Bayesian risk. As in, if we have a Bayes estimator which minimizes this whole term, then it also minimizes this term. And this in turn tells you something about this term. This is very broad. So let's talk specific properties. The first property I'm going to talk about is admissibility. It's a very straightforward frequentist property. It's also very connected to a property in game theory, which is total domination, strong domination. So admissibility, what do I mean by this? An estimator delta hat is inadmissible if there's some estimator which is just better in terms of frequentist risk. This is a frequentist term, admissibility. So what does it mean to be better in frequentist terms? So if there exists some delta 0 such that, well, first of all, it's not worse. So the frequentist risk of delta hat is larger or equal to the frequentist risk of delta 0, and so this holds for all theta 0, and it's better for at least one case. So there's this theta with where this inequality here is strict. So we have strictly larger in this inequality at least once. Because then we can just take the other estimator and we are happy from the frequentist point of view. So this is what inadmissible means, and then admissible just means that the estimator is not inadmissible. We can't find an estimator which is better. Admissibility is useful in the sense that we find estimators which we can discard. There's some estimators which we just shouldn't look at because they're inadmissible, at least from a frequentist point of view. And what's really nice about Bayes estimators is, if you look at this equation here, then you notice that if we have a Bayes estimator and it's unique, so this thing here is minimized for one and only one choice of estimator, delta hat, then there's no way to improve it for any single value. This is just kind of the intuition. For the actual proof, I just recommend looking at the book. I don't think the proof is in the book, but a very similar idea. So again, my textbook, I always said there's always going to be a link in the description. Please check it out. It has a lot of examples and very thorough explanations about pretty much everything that we do here. Anyway, if we have a unique Bayes estimator, it's also admissible. We're going to see the link to game theory in an example soon, but first I want to talk about the other property that's really important in frequentist statistics. I want to talk about minimexity. If we look again at the frequentist risk, we don't know the value of theta, and we can't just take the expectation of this because theta is not a random variable. So we would love to minimize this for every theta. But usually we can't, because there's a lot of values that theta can take, and one estimator might be better for the other and another estimator might be better for the first one. So we have to think about how to find a quote-unquote best estimator, because we still want to make a choice. This is not the problem that we have in Bayesian statistics, because the Bayes estimator is actually well defined, in the sense that we can always find it by minimizing this function, because we can just take the expectation over theta. Here we have theta which could be in a very large interval. So one way to go around this is to look at the minimax estimator. The minimax estimator is created by assuming the worst case. So it's defined as the minimum choice of estimator, where for any choice that we make, the worst case, so the maximum, is going to realize itself. So a very pessimistic view about the future. This is very useful for risk minimization. So if you have some program which is very risk sensitive, classical example is nuclear power plant. where you don't want a mistake to happen, even with a very, very small probability, because the effects of an error can be very drastic. Then you just assume that everything that can go wrong will go wrong. And this is what we mean by maximum here. So the theta, no matter what delta we choose, the theta that is going to constitute the worst case is going to appear. And even in that case, we want to be fine. And then this delta is defined to be the minimax estimator. This is closely related to game theory, because also in game theory, it sometimes applies that minimizing over this maximum is the same as first determining the worst case of theta, which, as it turns out, this is just a result. For the result, you can look for the proof to the result, you can look at the book, but it turns out that we can first just choose a prior distribution, which is really, really bad in the sense that it concentrates on the worst cases. So we first choose the worst prior distribution, and then we can choose the estimator, which minimizes this distribution. And now we just take the expectation. This is really nice, because this we've seen by the last slide. Delta is just going to be the base estimator given this pi here. So let's just call it pi star, which is the least favorable distribution. All of this is very abstract, so let's look at an example. Very common example, also from game theory, which is prisoner's dilemma. For people who don't know, two prisoners, let's call them Joe and Ernie, commit a crime together. They can't pull it off. They get arrested, and the police does not have enough evidence to make any one of them to prove that any one of them is completely guilty of the crime. So they give each of them a choice. Either they can confess, in which case, if they are the only ones confessing, they get out free, basically. So if they confess and the other player lies, and just because the other player wants to be loyal or something, then they get out. On the other hand, if the other player confesses and they lie, so if Joe confesses and Ernie lies, then Ernie is going to spend a long time in prison. 10 years. 10 years is a bit over the top. I don't know what crime I'm talking about here. While Joe gets free. On the other hand, if both confess, it's not great. That's a 6. And if both lie, it's a lot better than confessing, because the police has much less evidence, but they still have to go to prison for 3 years. The numbers are completely arbitrary. My point is, and that's usually the point of the dilemma, it is always, if these are your values, if you only care about the numbers right there, it's always the best choice to confess. Why? Either the other guy confesses, in which case I really want to confess unless I want to spend 10 years in prison instead of 6, or the other guy lies, in which case I still want to confess because then I get to be free. If I'm a total sociopath and don't care about the other guy. You might care about the other guy, then you have different numbers, and that is fine. But if we just judge by the table, it's always the best choice to confess, because the alternative, in game theory, we would say it's strongly dominated. Or strictly dominated, I don't know. I think it was strictly dominated. Actually, it doesn't matter. In statistics, we say the alternative is inadmissible. You have noticed this is not really an estimation problem. We don't have a sample on which we base our decision. But if we just say the true value theta is the behavior of our partner in crime, and again it's something between 0 and 1, then no matter what value theta is, if it's 0 or 1, we always want to take the decision delta of x, where x is actually nothing. We always want to take the decision to confess. The alternative to lie is inadmissible because our expected gain is always less. So this is a thing about admissibility. Now we're talking about Bayesian statistics, where theta is a random variable. And this is also a useful way to think about this dilemma. We can think about the probability that theta is, well, okay, I guess it's not really 0, 1, but it's confess or lie. Probability that our partner confesses. And based on this theory, we can make a decision. Now, we know the Bayes estimators, if they're unique, they're admissible. So without thinking, we already know what the Bayes estimator is. But what if I change the numbers around? Here we assumed that both people lying, it's pretty good, but it's not as good as me throwing the other guy under the bus. Because then I can get to go free. But what if the police actually doesn't have any evidence and it needs one of us to confess? So if we both lie, I get to go free. And then let's just move to free over here. This completely changes the situation. Because if I don't assume that the guy is lying, so if the probability that the guy is lying is very low, or it's very high, I should also lie. Or even if it's reasonably high, you can calculate the exact numbers. In the book there's an example where it's completely enough for us to believe that there's more than a 30% chance that the guy doesn't lie. That the guy doesn't confess, sorry. And that seems like a very reasonable assumption, unless we really don't trust our partner in crime. So actually, if we change these numbers around, suddenly this estimator of us lying can be pretty good. On the other hand, if it's very low, we probably shouldn't lie. But if we look at the min-max estimator, we're looking at the worst case. So if we lie, we assume that the other guy is going to confess, is going to throw us under the bus. Because here we are always assuming the worst case. And that might not be very reasonable. Sometimes it is, sometimes the costs are very high. But sometimes, if we're not completely sure, for example, that our partner is going to throw us under the bus, maybe in this game it's a good idea to lie instead of to confess. So the worst case assumption and it's not always reasonable. And this is what I want to end with today. Not with the advice that you should lie to the police. In this particular example, the numbers turned up this way, but it's just an example. I don't know what I'm talking about. Anyway, thanks for listening. In the next video, I'm going to talk in a lot more detail about the loss function and the estimation theory and the utility theory behind it.